This is going to be part 4 of a series of videos I'm making about doing some journal article reading about this article here, Microemulsions of Nonionic Surfactant. And so we're going to pick up where we left off. Where we left off was we were about to tackle the materials and methods section. And first, they're just giving us a list of the chemicals that they used and their abbreviations. Greater than 99, 98% purchased from Thermo Fisher, et cetera, all the way down. Isopropanol, 99.5, various different chemicals. One of the things I like to look for is were they purified? And there certainly were a lot of chemicals being used in this report. Let's see. Helium, doubly distilled water. Let's see. Purchase. Okay, so that's the last one. Then helium was purchased. Doubly distilled water from an in-house distillation setup was used in all experiments. Bridge 30 was dried at 105 degrees Celsius overnight before use. Dried means to remove the water. Notice the temperature there. All other agents were used as received. We typically use reagents as received in our research as well. And so not a lot there. But let's move on to preparation of microemulsions by surfactant titration. The surfactant titration method, so that's definitely something we're interested in, was used in all experiments. And then it's a reference right there. So we're going to have to look up reference 28 at some point. And let's just take a quick look at what reference 28 is. Reference 28, recovery of targeted hydrophilic compounds from simulated wastewaters using non-ionic microemulsion systems. I don't know if this has some of the same authors or not, but we'll circle that one as one that we want to get. And the temperature was always 25 degrees Celsius. A series of test tubes were first loaded with mixtures of ester and water, totaling 1 milliliter in all experiments. So I'm just going to write ester plus water. And spanning the full range of water mass fractions from 0.95 to 0.05 and 0.05 decrements, so decreasing. So let's see, so 1 milliliter with a mass fraction, and that's important. These are mass fractions, not mole fractions. So that doesn't require molar masses, but let's see. So one of these, if it was 1 milliliter, would be 0.95 milliliters. Let's see. Mass fractions, totaling 1 milliliter, which if it was pure water would be 1 gram, essentially. But then it says mass fraction, let's see, totaling 1 milliliter in all experiments. Anyway, so I think we will look at this later to see if it's actually 1 milliliter or 1 gram, see if there's very much of a density difference between the ester and the water. But so plus 0.05 milliliter, let's say, of water, all the way from 0.05 milliliters plus 0.95. So in every fraction in between, that's what I'm getting out of that. And could be grams. Could be grams. Something to look at. And let's just see here. Excuse me. Oh yeah, we got plenty of room in this, so I'll just keep it over there now. Water and ester densities at 25 were used to convert between mass and volume. The aforementioned water mass fractions correspond to volumetric ratios R between water and ester from 19 to 0.05. The dry non-ionic surfactant was added dropwise, that's the titration part, using Pasteur pipettes. And so Pasteur pipettes, I believe, are typically glass, into the water and ester mixtures with gentle manual shaking after each drop until 2 clear liquid layers were obtained, marking the formation of a Windsor 2 microemulsion. So let's see. So we have ester and water, and we're forming a Windsor 2, and the Windsor 2 would be water with microemulsion on top. Okay. It's not clear to me why. Let's see. So we would have to look at whether the ester and the water were soluble. Anyway, that's esters. Anyway, something to think about. Until 2 clear liquid layers were obtained. At this point, the test tubes were weighed on an analytical balance, Kern, blah, 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 with a precision of 1/10,000th of a gram, similar to the ones we have. And the mass of bridge 30 added was determined by difference. Titration with bridge 30 was continued until the whole mixture became a clear single phase corresponding to the Windsor 4 microemulsion. The total mass of bridge 30 added was also determined by weighing the difference. Okay, so that makes it sound like the ester and water, well, they're supposed to be insoluble. And so with gentle manual shaking after each drop, until 2 clear liquid layers were obtained, marking, okay. So wait a minute, so that means we have 1 layer until we have 2 layers. All right, something's not making sense. All right, but in the case of pseudo-ternary systems, the same, but it's what's clear is what they're doing is they're putting water and ester and water together in various fractions, and they're adding, so add bridge 30 until Windsor 2, then until Windsor 4. Okay, well, that's what they're doing. In the case of pseudo-ternary systems, where you have more than 3 things, the same procedure was applied with the only difference that water was replaced by mixtures of isopropanol and water with the mentioned volumetric ratios. Aqueous sodium chloride solutions, right, so they're basically changing the water phase. Buffers were prepared. Buffers were prepared by, yeah, keep reading, Bill, aloud. By slowly adding aqueous sodium hydroxide to aqueous phosphoric acid until obtaining the desired pH, measured with a stationary pH meter. All right. Next is construction of the ternary and pseudo-ternary phase diagrams of ternary and pseudo-ternary systems with some references were constructed using Origin Pro 8.5 software by plotting the data points corresponding to the compositions, mass fractions of mixtures that mark the beginning of the Windsor 2 and Windsor 4 domains, respectively. The mass fractions of the 3 components were computed with the formula mass fraction W equals mass of 1 component over mass of all the components. That's pretty straightforward. That's the kind of equation we like. Physical property measurements. The densities of the microemulsions were measured with an automated 4500 DMA density meter from Anton Parr, based on the vibrating tube method, with a precision of plus 0.00005 grams per centimeter cubed. The DMA cell was calibrated with dry air and doubly distilled water, while a built-in Peltier thermostat maintained temperature at 25 degrees Celsius. Cool. Refractive indices were measured at 25 degrees C using the sodium D line. A thermostated would mean temperature controlled, Abbey refractometer having precision of 0.0001. That's interesting. So this is not as easy a technique as we have accessible in our lab. And our lab goes plus or minus 0.00002, I believe, in units of refractive index. So far, so good there. We don't have the density meter that they're talking about. Electrical conductivity is recorded at 25 degrees Celsius with a conductivity probe, part of the Cobra 3 chem unit. Something in Germany. Before measurement, the conductivity cell was calibrated with two certified solutions, 84 and 1,413 microsiemens per centimeter. The uncertainty of the conductivity measurements was plus or minus 0.5%. Viscosities with a rolling ball microviscometer, also from Anton Par, equipped with a built-in Peltier thermostat. Peltier thermostats, we're running into those. They're basically, I don't know, you can look it up. They can heat and cool depending upon using electricity flowing in different directions. All measurements were performed at an inclination angle of 70 degrees. I will say this, the rolling ball microviscometer, rolling ball viscometers that I'm familiar with take a lot of volume. And they're only making 1 milliliter of solution. So all of these methods must have ways of doing them with very small amounts. Yes, using suitable calibrated glass capillary tubes with 1.8 and 3.0 millimeters. I guess that's probably the diameter, inner diameter. The relative uncertainty of viscosity measurements was less than plus or minus 2%. The Newtonian behavior of the systems was verified using different angles of inclination, 70 and 30 degrees. So a rolling ball with 70 and 30 degrees, I mean, it sounds like you're basically taking a tube and then putting the fluid inside and then allowing a ball to roll down it and timing it, and the times are calibrated. When identical viscosity values were obtained so at the different angles, so okay, what is a Newtonian fluid? A Newtonian fluid is a fluid that basically the speed with which you go through it doesn't change the viscosity, or the speed, yeah. I know if you pull up a non-Newtonian fluid video on YouTube, you'll see that if you smack a non-Newtonian fluid, if you hit it really hard, meaning you try and move through it very quickly, it is solid-like, but then you just sort of slowly go through it, and it's like a liquid. So they're saying this is a Newtonian fluid. Newtonian fluids are, Newtonian, so they are like liquids, let's say that. All right, the average size of micelle particles and their polydispersity index, this is something that's interesting, was determined using the Stokes-Einstein equation from dynamic light scattering, DLS, measurements of undiluted microemulsions using a Zeta Sizer Nano ZS apparatus. Measurement parameters were as follows, blah, blah, blah. I say blah, blah, blah because this is not something that we'll be able to do. We can currently measure viscosity in our lab of small sample sizes over a wide but not unlimited range. We are hoping to do density, and we can do refractive index. So And we can do the titration method. So far, I mean, we can probably do viscosities. We would like to be able to do, electrical conductivities. Interesting, and I don't know. Anyway, but we can do refractive indices, if anything, better. And we are hoping to do um, densities soon. Maybe, anyway, we'll think about that too. All right, extraction of tricyclic antidepressants, TCAs, into microemulsions. Actually, let's stop here because I think that's a good video. And this is mostly, to be honest, what we can do so far and what we're interested in.